Hello everyone, welcome to QChem webinar number 38. My name is Kuan-Yu Liu. I'm a staff scientist here at QChem in Pleasanton. Kevin Carter-Fenk is a graduate student in Professor John Herbert's research group at The Ohio State University. His project focuses on the development of scalable electronic theory methods and efficient calculation of properties in large systems. He has received a National Science Foundation REU Fellowship, American Chemical Society undergraduate awards in inorganic chemistry, and the most recent graduate research fellowship from Department of Energy. Today, he will be speaking to us about extended symmetry-adapted perturbation theory. Without further ado, I'd like to turn over to Kevin.
Thank you, Kuan-Yu, for the introduction. So today I will be talking to you about extended symmetry-adapted perturbation theory, a fragment-based approach to the calculation of noncovalent interactions. So first, I'll talk about some motivation. Why do we care to use such a method? And then I'll go over some fundamentals of symmetry-adapted perturbation theory. And afterwards, we'll go over some recent results using this method out of our group. And finally, we'll wrap up with how to use this in QChem and how to process the outputs of these calculations. So noncovalent interactions are ubiquitous in chemistry, from supermolecular host-guest synthesis to drug design. So they're useful in drug binding applications. And they also govern interfacial structure. So for example, here we have the organization of fatty acids at an air-water interface. So one of the most common approaches to calculation of noncovalent interactions is known as the supermolecular approach. So in this approach, we can compute the interactions by subtraction. So say your system has n molecules, then the interaction energy of that system can be calculated by first calculating the total energy of the entire system of n molecules, and then subtracting the sum of the monomer energies, the non-interacting monomer energies. So I have visualized this interaction energy of the water trimer, for example, and I have annotated each energy term here with the cost of the calculation. So the first term, the calculation of the supersystem energy, scales with capital N to the X. So the X depends on the level of theory applied, but say for a DFT calculation, that would be something like N cubed. And capital N here indicates that the calculation scales with the number of basis functions in the entire system. So you'll note that the notation changes for the monomer energy terms. So a lowercase n here indicates that the calculation scales with the number of basis functions on a particular fragment, or on the single water molecules in this example. So one problem with the supermolecular approach that's commonly encountered is that this calculation treats the monomer energy calculations on a different footing in terms of the basis set that's applied than the total energy calculation of the system. So the monomer wave functions are not calculated in the supersystem basis, leading to this basis set superposition error, or BSSE. So one way, so BSSE tends to, or BSSE does overbind interaction energies. So in order to correct for this, it's common to apply what's known as the counterpoise correction. And in order to do this, we compute every energy term with the same atom-centered basis. So every term now, you'll note, scales with the number of basis functions in the entire system in order for us to prevent this overbinding. And I've just notated that mathematically at the bottom of the slide, where the superscript corresponds to the basis set that's applied, and the subscript of the energy terms still refers to the system of atoms that are explicitly included in the calculation. So one way around this is via this fragment-based approach to non-covalent interactions. And the general strategy here is to take some larger system that may be intractable depending on the method that's applied to compute under the full supersystem basis, and break that system into discrete subsystems. So we can break up this water trimer in the graphic on the right. We have the density functional theory calculation on the supersystem, which should scale like the supersystem basis functions cubed. And we can break down the system into individual molecular fragments, which all scale with the monomer basis size. And we can, in this way, we can parallelize these calculations quite trivially, which leads to a speed up on this system of about a factor of 5, because we're able to do the monomer calculations separately. So the one caveat with non-covalent or with fragment-based methods is that when we break up the system like this, we no longer have the non-covalent interactions built into our system's wave function. So we need to add these after the fact, which brings us to symmetry-adapted perturbation theory. So some theoretical background on SAPT. As the name implies, symmetry-adapted perturbation theory is a perturbation approach to non-covalent interactions. It is formally a dimer theory. So in the SAPT formalism, all that we will consider are the interactions between monomers A and B. So the Fock operator in this approach is taken as a sum of monomer Fock operators. So these are the non-interacting fragments. And for a Fock operator of this form, we take a direct product ansatz for the wave function. So our zero order wave function to be used for the perturbation theory is taken to be direct product of the monomer wave functions, and this does mean that the monomers are not anti-symmetric with respect to exchange of electrons between fragments, but they are internally anti-symmetric, of course. So that anti-symmetry is built in as part of the perturbation. And this perturbation is really what we're interested in here. This is the intermolecular interaction operator, VAB. So this captures the interactions between the electrons and nuclei on fragment A with the electrons and nuclei on fragment B. And lastly, the terms WA and WB in the equation above are the molar-Plesset fluctuation operators. So these handle intramonomer correlation. So we can get MP2 correlation in the monomer wave functions through these operators. And the advantage then to treating these non-covalent interactions with a perturbation approach is that the perturbation expansion of the energy naturally unfolds into an energy decomposition analysis. So not only do we get a total interaction energy, but we also end up with various contributions that are intuitively understood as, so at first order, we get electrostatics, the interaction between the charge densities and nuclei in each fragment, and the exchange repulsion, which is a result of anti-symmetrizing the monomer wave functions. And at second order, we get induction and dispersion terms. So induction is the polarization response, and dispersion is your London dispersion. And the terminology SAPT 0 refers to a SAPT expansion with a Hartree-Fock reference state that is taken out to second order like this, because at second order, that is the first order of the perturbation series at which all of the interactions first appear. So you don't get, say, induction and dispersion at first order. So far, SAPT offers us natural energy decomposition, and it's free of BSSE because we are not computing our interaction energy as with the subtraction-based approach that was outlined before. We're computing it directly. One disadvantage is that Hartree-Fock reference wave functions tend to give large errors for hydrogen bonding because the Hartree-Fock reference state does not have the right correlation, and MP2 correlation tends to overestimate the dispersion term for the same reasons that molar-Plesset perturbation theory tends to overbind dispersively bound systems. Which brings us to SAPT KS, or Kohn-Sham. So one approximation we can make is to converge monomer densities using density functional theory to capture the intramonomer correlation in a cost-effective way, and then use the Kohn-Sham orbitals as our ansatz for the zero-order wave function. And this tends to improve the results for hydrogen bonded systems. So this is a figure from a paper out of our group in 2012, where HF here refers to the SAPT 0 reference state of the Hartree-Fock wave functions, and the PBE0 and long-range corrected omega PBE functionals were applied in the SAPT KS formalism. And you can see that, so this is for the S22 data set of dimer interactions at equilibrium geometries. And the hydrogen bonded systems errors are reduced in the density functional or the SAPT KS approach. However, what might pop out to you right away is that the blue error bars corresponding to the dispersion bound systems increase significantly when SAPT KS is applied, and though the dispersion errors are corrected a little bit in the long range corrected functional, they're not they're still not of benchmark quality. And what we can do about this is what we call the SAPT plus AID family of methods. So that stands for ab initio dispersion. So the dispersion is the least accurate term, and it's also the most expensive term to evaluate in the SAPT expansion. So the dispersion term costs n to the 5th, while the exchange dispersion term costs n to the 6th. So what we can do is use this empirical dispersion correction of the same functional form as Grimma's DFT-D corrections, but with a different objective here. So instead of looking to correct the long-range part of density functional correlation, we are looking to use this empirical dispersion formula for to capture the SAPT dispersion interaction, and that leads to that leads to some significant differences between Grimma's DFT-D dispersion and the SAPT dispersion. So let me briefly say here that these are summations over atoms in fragments A and B. So the I and J indices are nuclei in atoms A and or in fragments A and B respectively. So what we do is we replace the SAPT dispersion with the plus AID empirical dispersion potential. So we don't even compute those because they're costly and have large errors. And we still retain a term that can be interpreted as SAPT dispersion, but these empirical dispersion potentials are effectively free relative to the SCF calculations that need to be done, and they're more accurate than second order SAPT dispersion. And of note, the AID methods don't suffer from the double counting problem in the mid-range, as the Grimma dispersion the Grimma dispersion potentials have this double counting problem because the underlying density functional tends to capture mid-range intermolecular correlation to some extent, but in SAPT that's not an issue because the interactions are built in entirely at the end of the calculation. So we have our SAPT plus AID box here. So this XSAPT plus AID is a QChem exclusive feature, and we can get fast and accurate SAPT dispersion. And then let's address another issue where these SAPT expansions are based only on second order perturbation theory. So higher order effects may be important, and they may be particularly important in terms like the induction. So the we can apply what are called delta HF corrections to the second order SAPT induction to get an approximation for infinite order induction effects by taking a dimer energy that is calculated at the Hartree-Fock level. So that's the first term. And then subtract out the first and second order terms from our SAPT expansion, but without any dispersion, because the Hartree-Fock wave function does not have correlation. It cannot have dispersion interactions. So what this delta HF correction amounts to then is a correction for higher than second order polarization effects. And we can get even more accurate results with this treatment by replacing the usual SAPT induction amplitudes with induction amplitudes from coupled perturbed Hartree-Fock equations. So that I've notated here with induction response and exchange induction response. So those induction terms come from solving the CPHF equations, where the perturbation is the interacting monomer density. So these delta HF corrections are a pairwise correction to the induction energy. So we can get higher order corrections in the terms that need them the most. And however, this SAPT formalism, everything we've laid out so far, at least, has been entirely under this pairwise interaction approximation. So the pairwise approximation is the assumption that the interaction energy of the complex is a sum of the interaction energies between pairs of monomers. And in most cases, that is not a valid approximation. And because, again, in our water trimer example, the interactions between the dimer AB are influenced by the additional interactions with monomer C, and so on. So the truncation at two-body interactions is the pairwise approximation. And to leading order, this effect is dominated by, or the non-additive part of the interaction energy is dominated by polarization effects, especially in polar systems like water. So what we have done, what the X is in XSAPT, is the extended version of symmetry-adapted perturbation theory, where we variationally optimize the monomer wave functions with what is known as the X-pol approach, or the explicit polarization approach. And so in this graphic, I'm representing this with the optimization of the monomer densities in this system, where the electrostatic potential of the rest of the system is represented by atom-centered point charges. So this is an embedding approach to SAPT. So our monomer wave functions then have been self-consistently polarized by the electrostatic potential of the rest of the system. So that allows us to isolate the contribution of non-additive polarization effects. So we have variational non-additive polarization added to our benefits of the XSAPT plus AID approach. And so what do we do about the non-additive terms that are not leading order? So the non-additive dispersion, for instance, tends to not become important until the monomer sizes are at least moderate, but they can be, these non-additive dispersion effects can be important in systems as small as, say, the uracil dimer. Again, these empirical dispersion corrections are normally taken to be sums over atomic pairs, and this tends to overestimate dispersion energies in large systems, and in very large systems, this overestimation is dramatic. And what we have done recently is we've introduced a modified version of the many-body dispersion potential of Kachenko and coworkers to capture dynamic screening of the dispersion interaction at short range to engender our dispersion correction in SAPT with non-additive dispersion effects. The modified MBD potential is called MBD plus ESDQ because our MBD potential includes self-consistently screened dipole quadrupole terms, as well as the dipole response that is normally computed in MBD. And this potential was fit against high order benchmark quality SAPT dispersion data on a very extensive data set. So the most extensive data set that we've done so far for these dispersion corrections of a total of about 600 systems. So the data sets briefly are this pi 11 by 8 data set introduced by us. This is a set of 11 pi stacked dimers at 8 points along the intermolecular separation coordinate. And the S66 by 8 data set is a set of 66 dimers, again at 8 points along the intermolecular separation. And the X40 data set is a set of 40 halogenated molecules at the equilibrium distances. So XSAPT plus MBD then includes non-additive polarization and non-additive dispersion effects, and it tends to give us very high accuracy in large systems. So on that note, we'll transition to some recent results that we have reported with this method. Some that will feature are on this L7 data set of large systems. So these are 7, they're treated as dimers, and they have some high accuracy benchmarks available. So that it's a data set that is quite amenable to our benchmarking purposes. So these are DLPNO CCSD parentheses T benchmarks extrapolated to the complete basis set limit using tight thresholds, so as to achieve the best benchmarks that we could. And this plot represents the mean absolute errors of all of these different methods, and that all of the methods are color coded by the cost of computing the interaction energy. So the density functionals that I'll highlight in blue here are were chosen explicitly for their very good performance overall in the calculation of non-covalent interaction energies. And our XSAPT plus MBD method has the lowest errors overall and costs the cost scales only with monomer size rather than with the size of the super system. So our XSAPT plus MBD approach is cheaper than canonical DFT and affords better results with an energy decomposition attached. One other thing that I will highlight is that the many-body dispersion in these systems is a very important quantity to get right, because the XSAPT plus AID3, our best pairwise dispersion potential, expresses the highest error out of the XSAPT methods tested here for these very large systems. So some other applications here are to this DNA-ellipticine drug binding complex. So ellipticine, shown in the ball and stick representation, is a DNA intercalation drug, and the DNA backbone and bases are shown in just the stick representation. So we've computed the interaction energy using two of the best functionals for non-covalent interactions, and those are the B97MV and omega B97MV, and they're both counterpoise corrected results. And our XSAPT plus MBD procedure captures the total energy to within these DFT benchmarks quite well, and deviates only from the B97MV result by 1/10 of a kcal per mole. The wall time, however, is reduced by a factor of 2, because we're able to take this system of 3 fragments and break it down as such. So we can break it down into 3 discrete molecular fragments, and we benefit from that parallelization of the interaction energy calculation. So these are done with a triple zeta basis set. So there are a large number of basis functions in the system at 4600. And another thing to note is that the XSAPT energy decomposition that we get out of this produces results that are in line with intuition. So here, if we sum the electrostatic contribution, exchange, and induction contributions, we get an energy that is unbound. So this ellipticine complex does not bind to the DNA without the correction from dispersion. And a second very large system is this HIV-indinavir drug binding complex, where the indinavir drug molecule is the opaque ball and stick structure, and the HIV protease active site is represented as the translucent stick structures. This system is able to be broken down into 19 fragments and has almost twice the number of basis functions as the last system. So on our computational resources, we had difficulty obtaining canonical DFT results. So because of the requirement for a supersystem calculation in the supermolecular approach, but we were able to apply a triple zeta quality basis to this system with the XSAPT plus MBD procedure, and we get a result that is within the ballpark of these semi-empirical methods that were applied. So we have HF3C and PBEH3C results. And insofar as those are accurate, the XSAPT plus MBD comes quite close. And one very interesting thing that this reveals, in fact, with the energy decomposition is that though this system is still bound with the electrostatics and exchange and induction terms, the dispersion is most definitely non-negligible here at minus 137 kcals per mole. And there are no obvious pi stacking moieties here. It's just due to the very large system size and the extensivity of the dispersion interaction. And lastly, I'd like to point out that these AID plus ATM dispersion corrections include a 3-body correction to the dispersion. So these are sums over atom pairs and then sums over trimers of atoms. So just including 4-body and higher order effects, we capture an additional 20 kcals per mole of binding energy here. So in large systems, these non-additive dispersion effects are very important. Okay, so let's talk about how we use this XSAPT method. So we take our usual fragment input, and for those that don't know what this looks like, the charge and multiplicity of the total complex is listed first, followed by 2 dashes to indicate the start of a fragment input, and then the charge and multiplicity of each fragment follows in the standard notation of the dollar molecule section. So there are 2 fragments here. This is water dimer, and this is what the XSAPT REM input looks like. So you want to specify job type equals XSAPT, and long-range corrected functionals tend to perform the best for hydrogen bonding, and in general, they're the best for the SAPT KS approach. And if you are going to use one of these long-range corrected functionals, specify LRC DFT is true in the REM section, and also in the $XPOL section, indicate DFT LRC, and you'll also need a range separation parameter for each of the monomers. So notice we have 2 range separation parameters. These are the omegas in the omega PBE, and their units are in input in inverse millibor. So this corresponds to 0.385 inverse Bohr for each water molecule. And in order to obtain those range separation parameters for each fragment, we recommend this global density dependent procedure over IP tuning. So in order to optimize the value of omega for a given fragment, this is what the REM section should look like. You should start with omega GDD equals true and set an initial value of omega to 300. And then the corresponding level of theory is up to you, but it should match the level of theory applied in the SAPT job. So in terms of XSAPT options, what I showed you on the first slide detailing this input deck was a SAPT job without any embedding. But if we want to turn on electrostatic embedding to get that non-additive polarization contribution, you'll want to change the $xpol section from embed none to embed charges, and select the charges that you would like to use. So these options include Mulliken, Laudine, CHLP-G, and CM5 charges. Mulliken and Laudine charges are not recommended because of their instability with respect to the basis set that is applied. CHLP-G charges offer good results, but they tend to be far more expensive than CM5 charges. And CM5 charges, because they offer improvements in accuracy and efficiency of the calculation relative to CHLP-G charges, are the recommended. And those will be in 5.3. In the $SAPT section, there are a few options of note. So the algorithm keyword specifies which SAPT formalism to apply. So there exists an AO formalism of SAPT that is faster than the MO formalism because it reduces the amount of memory that's required in the calculation, and that the AO formalism does not have the formal SAPT dispersion. So if you're applying the AO SAPT, use an empirical dispersion correction. But if you want the full-fledged SAPT dispersion, then choose MO here. The order keyword specifies the order of perturbation theory to be applied. So we have the options of 1, 2, or RSPT. And first order will only yield electrostatics and exchange terms. Second order is recommended because it's the first order with all of the interaction terms. So and RSPT is Rayleigh-Schrödinger perturbation theory. This is the polarization approximation. So there are no terms from anti-symmetrization of the wave function. So that's more recommended if you're doing some careful analysis. So the basis keyword specifies the SAPT basis. So I'll go over each one of these really quickly here. The monomer-centered basis in SAPT corresponds to doing each monomer calculation in just the basis set of that monomer. The dimer basis corresponds to doing each monomer calculation in the basis of the dimer. So that allows for a more complete basis in SAPT. And if you're calculating the interaction of a dimer, the dimer basis is recommended because it minimizes basis set incompleteness error. And the monomer basis is generally not recommended for that reason. because it's a less complete representation of the space. And the projected basis is a basis in which it generalizes sort of the idea of a dimer basis to extend to systems of multiple fragments. So say we had 3 or 4 or more fragments, then the projected basis is recommended because it does all of the calculations for SAPT in the monomer basis. So for all of the monomers, their calculations are done in the monomer basis. But for every dimer calculation, the Fock matrix is constructed in the dimer basis rather than the monomer basis, giving it some more flexibility. So this empirical dispersion command options can be set as 1, 2, 3, or 4, and I'll go over those right now. So option 1 for the empirical dispersion is AID. So that's the first generation empirical dispersion correction that we introduced, and that is not recommended because it was fit to reproduce total interaction energies and not to reproduce SAPT dispersion. So therefore it absorbs errors from other terms. So it can't be really trusted to represent SAPT dispersion. AID2 is the second generation empirical dispersion method, and that is fitted to high order SAPT dispersion data. So that can be trusted as a purely SAPT dispersion correction. And AID3, which is recommended over AID2, is the second generation of AID2. So that AID3 correction was fitted against just a larger data set. The MBD potential is recommended for all systems in general, because if your monomers are not small but not too large, sometimes the many-body dispersion correction can be important. So and MBD tends to retain its excellent performance even in small systems. So it's comparable to AID3 results in small systems. It's also density dependent. So it's more ab initio than the rest of the empirical dispersion corrections. And it captures these non-additive effects in large systems. So for large monomers, it's definitely recommended. So moving on to applying this delta HF correction for pairwise induction, the method keyword in the REM section is set to HF, and that specifies that we're going to do a Hartree-Fock reference wave functions, and embed is set to none, so there's no electrostatic embedding here, just the dimer is involved in this delta HF correction, which I guess I'll note now that this delta HF correction is only available in the dimer basis, and that's primarily because we use a counterpoise corrected Hartree-Fock dimer energy in that equation. And to turn on the delta HF correction, use the DSCF keyword, and just the presence of that keyword triggers the delta HF job. An optional keyword, but one that may improve your results, is the CPHF keyword, and that specifies that the induction terms will be replaced with their coupled perturbed Hartree-Fock induction for a bit of a better correction here. Okay, so on to interpreting the output. So on the left, we have a SAPT job that was done with no electrostatic embedding. And on the right, this is an output from an XSAPT job that was done with CM5 charges for the embedding. So the pairwise interaction terms come from the SAPT output. So in our construction of the XSAPT plus AID interaction energy at the bottom, we just sum over these terms from the SAPT output. And then in order to get the correction from variational polarization, we take the SAPT corrected total energy from our embedding job and subtract away the SAPT corrected total energy from the gas phase job, and that offers the corrections from variational polarization in the monomers and in the interaction potential. And I've shown just a snippet here of the output for the delta HF correction in red, and that is the delta SCF energy that's printed here is our delta HF correction. And this altogether, the green, blue, and red terms, are the total XSAPT plus AID interaction energy. And I will also note that normally the total induction of this method is taken to be the sum of the pairwise induction terms, so induction and exchange induction, and the blue and red terms. So because these are all corrections to the induction, be it non-additive corrections or pairwise, that's usually taken to all mean induction in the XSAPT plus AID family of methods. So I would like to acknowledge my group, and in particular, I'd like to thank John Herbert for being an excellent advisor, Dr. Kaun Lau, who's just starting at Virginia Commonwealth University as an assistant professor, and Dr. Kuan Yu Liu, who is now with everyone at QChem, for their contributions to this work, the Department of Energy for funding QChem for being an excellent software package, and Ohio Supercomputer Center for computer time. Thank you.
Thank you, Kevin. So we got our first questions. Have you tried to incorporate couple cluster theory into SAPT?
No, we do not have these coupled cluster intramonomer correlation corrections that I think you're talking about. Those aren't not available in QChem.
Okay, probably related to that question. So what's the largest system you have tried, and how does the cost for the super system method and the XSAPT?
So I guess the cost comparison is a little bit difficult for the largest system that we've tried. Is this, if I may go back, the HIV-indinavir complex here. So we were actually unable to obtain super system DFT results. But at least in systems like this DNA-ellipticine complex, we see factor of 2 speed up.
Cool. So I got a question. So so for the user input, so can I summarize like this? So the user have to do 3 calculations. First, have to do the tuning for the long range DFT parameters. Then second step, do the regular XSAPT calculation, and finally need the delta HF to do the corrections. Is that right? You have to do the 3 separate calculations.
Yes, that's correct. There's actually one more calculation, and that is the gas phase calculation. So let me get back to this slide. So these are the 3 SAPT jobs that need to be run. So without embedding, and then with embedding and DHF.
So there are actually 4 steps, right?
That's correct.
Okay, cool. Okay, we've got more questions. So what about the SAPT for the electronically excited states?
For electronically excited states.
Like the excited.
So right now we don't have an implementation for electronically excited SAPT.
Okay. Well, the next question is this XSAPT compatible with ECP?
That's a good question, and I believe the answer is no. The effective core potentials are not available right now.
Okay. So there is a similar question. So for the, I guess that's similar to the excited states questions. So what is your opinion of XSAPT to be used in the microsalvation?
In microsalvation?
Yes. Maybe we need more information from these questions.
Yeah, I can't say I'm completely familiar.
Please add more information in the question box. I'll present to the speaker. So we got a question for the protein ligand binding systems. And I think the first question is, how is the protein partition performed?
That's a good question. So so long as the fragments are not covalently bonded, you can specify these as individual molecular fragments. So what we would do in the case of this HIV protease active site is find the important residues through whatever may be your favorite method for doing that, and then cut out the active site, and you need to make sure that your individual fragments are not covalently bonded. So the reason for this is that the symmetry-adapted perturbation theory breaks down in just as normal perturbation theory would break down in terms of the perturbation being too large. So a covalent bond is too large of a perturbation.
Okay. So back to the microsalvation is a way to adding water molecule explicitly to mimic the solvated environment. So I guess the original question can be rephrased as what's your opinion of the XSAPT to adding more water to simulate the solvated environment?
Okay, so for that, I think it should be quite an excellent approach, because your water molecules act as really nice discrete fragments, and XSAPT has shown really good performance for water clusters. That reference, I think, is in this the AID3 reference. Yeah, this JPhys Chem 2015 paper. There's some sizable water clusters that were done with XSAPT with really low error bars compared to some benchmarks. So I think for microsolvation applications, it would really thrive.
We'll move to close the webinar here. If you have questions later, feel free to contact me. I'd like to first thank Kevin for the great talk. I also want to thank all the attendees for listening and participating. The recording will be posted on YouTube for the next few days. And please give us your feedback. Really appreciate it.
This concludes our webinar. We would like to thank Kevin Carter-Fenk for his excellent presentation, as well as Kuan Yu Liu for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.